Hey, astronomy class. Hope you guys are doing great today. In our lesson today, we're going to be answering this question a little bit more. What is happening in the universe? And I want to talk a little bit about that today. So I'm going to jump right in so we don't waste time. We have a shorter school schedule, and I'm really excited about that. Our last day will be May 14th. And that also means that the things that I was planning on discussing with you guys and learning about, we're going to have to kind of smush them together a little bit, and we're not going to get a lot of details. We're just going to kind of go big picture. So that's what we're going to do today, is just kind of look at some big picture things of what's happening in the universe and fast forward a little bit about what we've been learning about. So just to review real quick, when we study the sun, we learn that it produced energy by fusing atoms together. That's where energy comes from the sun. Energy gets released when atoms are fused together. And it's going to be important this week to think about what kinds of atoms they are, and you'll see why later. What were the names of these atoms that were being fused in the sun? Do you remember? What are the names of the atoms being fused in the sun? So, what is getting fused into what? The answer is hydrogen gets fused into helium. Second question, what do we need for fusion to occur? What do you need in order for there to be nuclear fusion? What do you need on Earth, or what do you need on the sun in order for it to happen? What two quantities need to be really, really high? The answer to that is high temperature and high density. You need to have something really, really hot so that its atoms are moving fast, and then something that's really, really dense so it's packed in real tight. When you have those two things, it's possible to have nuclear fusion happen, and that releases energy. And then number three, what two forces keep a star stable? There are two things that are acting against each other that keeps the star stable. What are those two forces? And the answer to that would be gravity and the pressure that comes from fusion. So gravity pushes in, pressure from fusion pushes out. Okay, so just another review. High mass stars versus low mass stars, it makes a big difference. Basically, high mass stars burn through their fuel a lot more quickly than low mass stars. And so, therefore, high mass stars, yes, they have more fuel available, but they need a lot of fuel to keep going. Whereas low mass stars can last much longer, even with less fuel. Okay, so what we're going to do today is just look at our model of a star. Remember, in science, we use models to kind of explain what's happening, and it also helps us make predictions about what's going to happen. So let's look at our model of the star. Here is a star. The outer layers of it are made up of hydrogen. Hydrogen is the smallest and lightest element in the universe. It's also the most common element. And on the outside edge of a star, it's mostly cool hydrogen, and then there's a core where hydrogen is getting fused into helium. Okay, only in the core does that happen, because only in the core is it hot and dense enough for there to be fusion. So this is our model of a star. Very simple so far. We're going to add some layers to this to make it a little bit more realistic of what a star is actually doing, because you got to think, um, mass just doesn't disappear. It has to be going somewhere. So whenever you fuse two hydrogen atoms together, or really, I guess it's four technically, get fused into one helium atom, that new helium atom has to go somewhere. And so I just answered this question, but what is hydrogen being fused into? It's being fused into helium, and that helium is useless. We stars like our sun, they can't use that helium, so it just kind of builds up like ash in a fireplace, and it builds up in the core. And because it's heavier than hydrogen, it sinks to the center. Right? I mean, heavier things, more dense things will sink. So the helium that gets newly created in the star's core will sink to the bottom, sink to the center, and you end up with this kind of dead weight in the star's core, dead weight made up of helium. So this is what a star will do, and our sun has been doing this for, our models predict, about 5 billion years. Our sun has been taking hydrogen and fusing it into helium. So by now, our sun has a pretty good size helium core of just dead weight, dead helium ash. So this is kind of a model to show what happens to a star over time. So at the very beginning of a star's life, it'll take the hydrogen that's burning in its core. We call it burning. That just means fusing. It's just a way that we talk about fusing. So hydrogen burns in the core, and over time that leads to helium building up inside the core. And so we have a helium core, and then we call this around the core, we still have hydrogen fusion happening. And so we call it a shell. Kind of like a turtle has a shell around the body of the turtle. So the shell kind of surrounds the turtle. Well, the same thing is true with a star. You have the core of the star is now made up of helium, dead helium atoms, and then the hydrogen surrounds that and continues to fuse in that shell around the helium core. So this is our new model of a star. All stars on the main sequence do this. They take hydrogen, fuse it into helium, and then end up having this shell of hydrogen fusing around a dead helium core. So let's return to this picture again. So over time, if we let time play out here, if we let time move on, this is not to scale either. Hydrogen fusion and the helium core are much, much smaller than the overall star. But as you let time go on, what's going to happen? What would you predict happens as time goes on here? So as time moves on, hydrogen continues to fuse. That's really the only thing that's happening is hydrogen is fusing right here. The other things aren't really doing anything. The cool hydrogen is just sitting there. The helium core is doing nothing. And so over time, hydrogen fuses into more helium, and that helium core will grow. Is that the prediction you made? The helium core continues to grow and grow until it finally overtakes the hydrogen fusion that happens, and there's no more hydrogen that's hot enough to fuse. So let me say that again. Over time, the helium core grows until there's no longer any hydrogen left to fuse. There's cool hydrogen out here, but it's not hot enough to fuse. So what will happen to the star now, according to our model? Remember, our model has forces happening inside of a star. What's going to happen to this star now that there's a helium core that's not providing any energy, not providing any pressure? What will happen next? All right, if you made the prediction, this is what should happen next. Since there's no more pressure pushing outward, remember a star usually has gravity pushing in, pressure pushing out, but now there's no pressure pushing out because there's no fusion. So what happens next is the gravity will start to contract this ash, this helium core of just dead ash. And so gravity contracts it and makes it hotter and hotter. And eventually it makes it really, really hot enough to start fusing helium into something else. So on the main sequence up here at the top, hydrogen fuses into helium and releases energy. But whenever helium is pushed together, if it's hot enough, it can actually fuse together to make carbon. So helium turns into carbon next. But the problem is this requires 10 times more temperature and speed. And so once a star reaches the point where it's run out of hydrogen to fuse, then it starts to fuse helium into carbon. And this becomes our next phase in the star's life. The helium core contracts and gets hotter. And as it gets hotter and dense, it starts to allow the helium to fuse. Technically, it actually creates enough heat at the core here to create hydrogen fusion again. The hydrogen that's surrounding the core gets hot enough again to start fusing. And so you get this extra fusion happening here. And because there's extra fusion, there's extra pressure pushing out on the star's core, and it causes the star's outer layers to expand and cool. And the helium core continues to contract, and the temperature continues to rise, and that allows for helium to fuse into carbon. So that was a lot that happened just then, but basically what you need to know is the hydrogen fuses into helium. The helium can't do anything until gravity contracts it further and heats it up, and then helium fuses into carbon. So then you've got this extra step happening here where you have hydrogen fusion happening in the shell and then helium fusion happening in the core. So all of that's going on now. And so you end up with this carbon core that's now dead and useless. Instead of the helium core being dead and useless, now you have the carbon core dead and useless. And this is the new phase of the star's life. We're no longer on the main sequence anymore because now the star has expanded. It's got extra energy happening down here. Because there's extra energy, there's more pushing outward force, and that's pushed the star's outer layers here to expand. And when you expand the star's outer layers, they cool down and they become redder. And so that's what's happening here. And this is another model of that. So you got carbon, a dead carbon core. You got the helium in a shell around that. You got the hydrogen fusing in a shell around that, and the expanding outer layers. And so you might guess what this phase of the star's life is called. No, it's not Pac-Man. This star is now a red giant. So when a star is fusing helium in its core, it produces so much energy that the outer layers expand and cool, and the star enters the red giant phase. So the red giants, we talked about those already. The giant stars, where do they come from? They're actually stars that have ended their adult lives and they're now into their old age. We might call them the senior adult part of a star's life, the oldest part, and the star is getting very old. This is the red giant phase. So if you look back at our main sequence again, remember stars started out at the top right as a nebula. They contract and become new baby stars right here on the main sequence. They begin fusing hydrogen into helium, but over time they run out of hydrogen to fuse and they start fusing helium, giving off more energy, making the stars bigger, and they become giants. So this is the track that a star will follow on the main sequence to the giant phase. So here's a little picture that I like to look at to show a prediction of what will happen to our sun. And now I think Jesus will come back before all this happens, but who knows? This is what science predicts will happen with the sun if all things were left the same and our predictions and models are accurate. The sun will after it is finished fusing hydrogen into helium, the sun will become a red giant and will overtake the Earth. So here's today, and then later. Oh no, too far. Later, the sun will expand and overtake the Earth and become a red giant. Here is a prediction of what the size will look like for the Earth at its fullest. For the sun. At its fullest expansion, the sun will be as large as 2 AU across, which is 2 times the radius of Earth's orbit. Down here is the sun, this little yellow dot. That's what the sun is today, and the sun will expand into this giant red giant star when it gets to this phase in its life. Just a couple of facts about what our model predicts. The main sequence phase for our sun lasts about 10 billion years. We've already said that. But the red giant phase is much, much quicker. It's about 100 times quicker. It only lasts 100 million years, which seems like another absurd amount of time. But in astronomy terms, that's pretty quick. So the sun lives on the main sequence for most of its adult life, and then when it becomes a senior adult, when it runs out of helium or runs out of hydrogen to fuse and starts fusing helium, enters the nursing home of the red giant phase of its life. And even this doesn't last forever. So once our sun fuses hydrogen into helium, and then starts fusing helium into carbon as a red giant, this will also end because the star will run out of helium to fuse. So just like the star ran out of hydrogen to fuse, then the star will run out of helium to fuse, and eventually the carbon core will start to take over. And low mass stars don't have enough gravitational energy to fuse carbon into heavier elements. So once the carbon core takes over, this is the end of a low mass star's life. And then there will be some final explosions that happen that cause the outer layers to expand and kind of float away. It's kind of like a slow motion explosion, but it's a real thing that happens. And so once the star begins to fuse carbon and the carbon core starts to take over, when the carbon core takes over and wins, the star just kind of drifts into death. and it leaves us with some amazing results. It's called what they call it a planetary nebula. It's a terrible name, but basically it's saying that it's the name of what happens to a star once it dies and slowly kind of fades and drifts apart and gets ripped apart slowly. This is a picture of one of them. What an amazing picture! This is the death of a low mass star. It's called a planetary nebula. The outer layers of the star just drift away and produce some incredible pictures. Here's another one called a planetary nebula. Just an amazing picture. This is a dead star. Here's another called a planetary nebula. Again, when a star dies, this is what we get as a result. Here's another picture of a planetary nebula. Just amazing pictures. Here's one more. Just incredible. I mean, you can see different things happening in each one. Each one is unique. Remember, we've already read a verse in 1 Corinthians 15 that every star differs from each other, one glory to another, and we can definitely see that in space. I like this one too. One more little fact here. This is what happens to low mass stars, and we didn't say what happened to the carbon core. But the leftover dead carbon core gets extremely condensed by gravity into a white hot ball of carbon atoms called a white dwarf. So this is what a white dwarf is. This is the leftover piece of the star's core. So the outer layers expand away, and that's what this picture shows here. The outer layers have expanded and kind of slowly exploded away, but the leftover core, and you can see it right here, this leftover core is a bunch of like a big ball of carbon atoms, and they're super condensed, super hot, white hot, and it's inactive. It's not fusing or anything like that. This is the final state of all stars, smaller than 10 solar masses, and that includes 97% of all stars will end this way. A lot of them haven't ended yet because low mass stars are very fuel efficient and they're still running strong. But our models predict that this is what the end is like for almost all stars. They become a planetary nebula. The outer layers become a planetary nebula, and the core, that small carbon core, becomes a white dwarf. So if we wanted to just kind of put a picture to it here, like a little timeline of a star's life, starts out as a nebula, and that nebula gets condensed into a bunch of stars usually. Some of them are low mass stars, some of them are high mass stars. Okay, so the nebula becomes a bunch of stars. The high mass star will die first and become a red supergiant. And for the same reasons, the high mass star will run out of hydrogen and start fusing helium, and that extra energy pushes the star and expands it and cools it down. So that's what happens first. But then the low mass stars, when they die, they become red giants. And we talked about what happens next. So a red giant, what happens next for a red giant is it becomes a planetary nebula and expands and dies. And then that leftover core, that little piece right here, this leftover piece is called a white dwarf. And these sizes are not to scale at all, right? But they show us, give us a good idea of what happens to the low mass star as it reaches the end of its life. So that's the track of what will happen to a low mass star. And then tomorrow we will look at what's going to happen to a high mass star. They can do a little bit more because they have more gravity. They can fuse carbon into other elements. So it has a different track. But this is what happens to low mass stars as they reach the end of their life. This is what's happening in the universe. Things are changing from low mass stars to giants to planetary nebulas to white dwarfs. So I know that was a lot, but that gives us an overview of what's going on in the universe.